Have you ever stopped to think about what really happens the moment an airplane touches the ground? In just a few seconds, tires that were completely still suddenly spin faster than 180 miles per hour, holding the weight of more than 300,000 pounds. In that instant, engineering is pushed to its limits, and even the smallest mistake could put an entire aircraft at risk. So what allows a tire to survive forces like this without exploding? Every year, millions of aircraft tires are built in highly specialized factories, following a process where every step is measured down to fractions of a millimeter. Today, we are going inside this world to see how a tire is made to withstand 300,000 pounds at nearly 200 miles per hour. If you enjoy understanding how things are made and seeing real engineering in action, subscribe now and get ready to discover the process behind one of the toughest components in modern aviation. During the landing of a commercial aircraft, the pressure on each tire reaches levels that very few materials on Earth can handle. A large jet instantly transfers more than 300,000 pounds of weight to the landing gear. In seconds, the tire goes from zero movement to spinning at high speed. This sudden transition generates heat, friction, and intense deformation, demanding a structure with exceptional precision and strength. Heat is one of the biggest challenges in aviation tire design. The outer rubber can reach temperatures above 480 degrees Fahrenheit, while compressed air inside the tire must remain stable and controlled. That difference in temperature and pressure requires special compounds that can expand without losing stability. If that balance fails, safety is compromised. Impact absorption is another critical point. Aircraft tires must handle constant changes in weight, temperature, and speed. They are built with multiple layers of synthetic rubber reinforced with nylon and steel fibers, allowing controlled flexing without tearing. Each tire must withstand over 40,000 pounds of pressure again and again without losing shape. Understanding these forces is the first step to understanding how these tires are made. Every decision, from rubber composition to internal reinforcement to pressure control, is based on the need to perform under extreme conditions. But before a tire ever touches a runway, it has to be created with microscopic precision in a controlled environment where material science sets the limits of strength. The process begins with choosing the compounds that form the base of the tire. Each ingredient is selected for specific properties like elasticity, heat resistance, and chemical stability. Natural rubber is still used, but in controlled proportions, combined with synthetic polymers developed in labs. These materials are mixed in heavy-duty industrial mixers capable of processing tons of material with exact precision. Additives like silica, carbon black, and metal oxides strengthen the rubber's molecular structure, creating a dense matrix that can stretch without breaking and resist extreme heat. The goal is not just to hold the weight of the aircraft. It is to perform safely under rapid temperature changes and high-speed stress. Along with rubber compounds, the mix includes steel wire and technical fabrics like nylon and Kevlar. These act as structural reinforcement, distributing force across the tire. Steel provides rigidity, while Kevlar and nylon offer controlled flexibility. The result is a balance between strength and weight, essential for durability and performance. Throughout this stage, sensors continuously monitor viscosity, density, and temperature. Even tiny variations are corrected immediately, ensuring every batch maintains precise physical and chemical properties. That consistency is what makes aircraft tires reliable under extreme real-world conditions. Once the rubber mixture is ready, it moves on to form the tire casing, the foundation of the entire structure. This step defines strength, shape, and shock absorption. The casing is assembled layer by layer, with each layer serving a specific purpose, such as support, flexibility, and grip. Sheets of reinforced rubber are wrapped around rotating drums, forming the basic body of the tire. Between these layers, nylon and Kevlar fabrics and braided steel cords are placed. These fibers act as an internal network that prevents deformation under intense load. Their angle and placement are calculated through structural simulations to ensure even force distribution during landing. Dimensional control is strict. Every layer is measured with exact precision, and any deviation means starting over. Even the tire's profile influences aircraft stability during takeoff and landing. An incorrect shape can cause vibration and imbalance, so each detail follows strict aerospace standards. At this point, the tire has volume and form, but its layers still behave independently. It is ready for the next step, the precise cutting and assembly that gives the tire its final geometry. The partially built tire now moves to one of the most delicate stages, cutting and assembling the final layers. Thick rubber sheets are rolled out over heated cutting tables to maintain ideal texture. Laser sensors measure thickness and width with exact accuracy. The smallest deviation can affect balance and safety during landing. Layers are stacked in a controlled sequence. Internal layers receive synthetic fabric and steel reinforcements for stability, while outer layers use high-density rubber designed to withstand abrasion and heat. Hydraulic rollers compress each layer, eliminating air pockets and creating a flawless bond. Quality checks are strict. Technicians inspect density, thickness, and alignment. A tire must be perfectly symmetric to endure repeated landings. If any flaw is found, it goes back to the beginning. This precision guarantees that a tire produced today performs just like one made years ago. After this stage, the tire has its final shape but not its final strength. Next comes the step where heat and pressure transform the raw structure into a unified, high-performance component. The completed assembly enters a steel mold that defines its final shape and tread pattern. The mold closes under pressure, and superheated steam flows through internal channels. The combination of heat and pressure triggers chemical reactions in the rubber, linking molecules and turning the layered structure into one solid piece. This process, called vulcanization, changes the rubber from soft and workable to elastic, durable, and highly stable. Temperatures climb above 330 degrees Fahrenheit, and internal pressure ensures every detail of the mold is captured. The timing is calculated based on rubber composition and thickness to prevent overcuring or undercuring. When the cycle ends, the mold opens, and the tire emerges hot but fully formed, tread, texture, and technical markings all in place. Layers that once acted independently are now a unified and extremely resilient structure designed to handle massive pressure and repeated impact. Each production batch undergoes destructive testing and chemical analysis before being approved. Only after passing these standards does a tire move on to dynamic testing, where it faces the same forces it will encounter in real flight operations. With the tire complete, one of the most important phases begins: the resistance tests. Each model is subjected to simulations that recreate real landing and takeoff conditions. Test chambers reproduce the impact of an aircraft touching down at more than 180 miles per hour. Sensors installed at different points measure deformation, temperature, and the behavior of the rubber under compression. The goal is to confirm that the tire remains stable even under forces that exceed several tons per square centimeter. Speed testing is the most demanding stage. The tire is mounted on equipment capable of spinning it at extreme speeds, while internal pressure gradually increases. In some cases, engineers intentionally push the material to failure in order to identify the exact breaking point. This data is essential to fine-tune the rubber composition and vulcanization parameters, ensuring the final product operates with a wide safety margin. Another crucial test is temperature resistance. During landing, friction with the runway can heat the tire surface to more than 480 degrees Fahrenheit. To simulate this scenario, the tire is gradually heated while spinning under maximum load. Thermal stability and heat dissipation determine whether the compound meets expected performance. The rubber must withstand high temperatures without losing elasticity or breaking down internally. Finally, tires are inflated with nitrogen for sealing tests. Nitrogen is chemically stable and does not react with rubber, ensuring consistent pressure at different altitudes. All these tests determine whether the tire is suitable for commercial or military use. Only after passing every stage is it cleared for final inspection, where advanced X-ray analysis checks its internal integrity. After the resistance tests, each tire goes through a detailed inspection to ensure there are no internal flaws. Quality control uses X-ray and ultrasound systems capable of detecting imperfections invisible to the naked eye. These tools create three-dimensional images showing the internal structure of the rubber, fiber placement, and condition of the steel cables. Any irregularity such as air pockets, delamination, or microcracks is identified before approval. The analysis takes place in controlled environments with regulated temperature and humidity to avoid variations in results. Specialized technicians review the images and classify each tire according to aviation standards. Any tire that does not meet requirements is immediately rejected, since there is no room for error in air safety. Every record is archived digitally, creating a traceable history of the entire manufacturing and inspection process. In addition to imaging exams, random samples are cut and analyzed in the lab. These sections reveal layer distribution, rubber density, and fiber alignment. This ensures uniform structural quality in compliance with international standards such as FAA and EASA regulations. Consistency is essential so that entire aircraft fleets operate with the same level of safety. Only after passing this exhaustive evaluation is the tire approved for installation. The final inspection confirms it can handle the load, heat, and pressure for which it was designed. Each unit represents hundreds of hours of testing and verification, reflecting the precision and reliability aviation demands. The next step is integrating the tire with the wheel assembly, where steel and rubber come together to form the aircraft's landing system. After approval, the tire moves on to the wheel assembly stage. This process requires absolute precision. since it involves fitting rubber onto aerospace-grade aluminum or titanium wheels. These wheels are built from lightweight yet extremely strong alloys that can absorb impact and dissipate heat quickly. Before mounting, each component is cleaned with specific solvents to ensure perfect sealing between the rim and the tire. Installation is done using hydraulic presses that apply uniform pressure across the assembly. Valves and locking mechanisms are then adjusted to guarantee full sealing. The tire is inflated with nitrogen, an inert gas that does not react with rubber and helps maintain stable pressure during temperature changes. Pressure settings vary depending on the aircraft type, maximum takeoff weight, and operating conditions. Next comes balancing. This step is essential to remove vibrations that could affect performance during takeoff or landing. The assembly is rotated in precision machines that measure weight distribution. Minor adjustments are made until perfect balance is achieved. The result is a system that combines mechanical strength with dynamic stability in any runway condition. Once balanced, the tire and wheel are attached to the landing gear, forming one of the most robust systems in aerospace engineering. From here forward, every landing becomes a real-world test where steel, rubber, and physics work together. But the story does not end here. When the tread wears down, the tire returns to the factory for renewal and retreading. When a tire reaches its wear limit, it is not discarded. The internal structure remains intact and can be reused several times through retreading. First, the tire is carefully inspected to confirm the casing has no structural damage. Then, the worn outer layer is removed using controlled buffing equipment. This process removes only the used rubber layer without affecting the internal structure. After buffing, a new rubber layer is applied with precise thickness control. This layer goes through vulcanization again, restoring elasticity, grip, and heat resistance. The result is a tire with performance equal to a new one but with lower cost and reduced environmental impact. Retreaded tires are subjected to the same pressure, temperature, and speed tests as new ones. Each unit must meet the same safety and performance standards required by aviation authorities. In many cases, a commercial aircraft tire can be retreaded up to 7 times before final retirement. This process represents a major step towards sustainability in aviation. It reduces raw material consumption, decreases waste, and saves energy resources. It shows how modern engineering can combine technology with environmental responsibility. Even after hundreds of flights, an aircraft tire can return to the runway ready to face extreme forces once again. The scale of aircraft tire production and operation is impressive. A Boeing 777 uses 14 tires, while an Airbus A380 needs 22 to support its full landing weight. Each tire can cost between $5,000 and $20,000 depending on specifications. Even with this price range, durability and retreading capability make them a cost-effective investment for airlines prioritizing safety and operational efficiency. During landing, surface temperature can exceed 480 degrees Fahrenheit, similar to industrial friction heat. Yet the material is designed to handle dozens of landings before significant wear appears. In normal conditions, a tire can accumulate more than 90,000 miles of runway use across multiple flight cycles. Manufacturing is so precise that each tire receives a serial number and full traceability record. This includes production date, material composition, and number of retreads. This traceability is essential for fleet maintenance and safety control. Behind every smooth landing, there are years of research and testing. Aircraft tires represent a balance of flexibility, strength, and precision. They are a clear example of how advanced engineering transforms raw materials into highly reliable technology capable of surviving extreme conditions. From the first cut of rubber to the moment the tire touches the runway, this journey highlights the power of modern engineering. Each tire is the result of thousands of calculations, tests, and inspections, ensuring that aircraft weighing hundreds of tons can land safely. What looks like a simple rubber ring is actually one of the most advanced and reliable technologies in aviation. The retreading process also shows how science and sustainability work side by side. Extending tire life reduces waste and preserves natural resources. Every retreaded tire means less environmental impact and greater efficiency. Next time you feel the wheels touch the ground on a flight, remember everything happening behind the scenes. Years of development, precision tests, and engineering excellence come together in that moment, turning raw materials into safety and reliability for millions of passengers. Now tell me in the comments, did you know aircraft tires were this complex? If you enjoyed learning about this incredible process, like the video, subscribe, and turn on notifications to keep exploring the world of industrial engineering and manufacturing with me.